Imagine a detective on the hunt for a silent, invisible killer. One that can sweep through an entire city in just days, leaving clues that only a trained eye can spot. Well, this isn't a crime novel, it's the real world of epidemiology. So, let's follow the evidence and see just how these medical detectives crack the case.
You know, Rudyard Kipling might have summed up the job description perfectly right here. For an epidemiologist, these 6 simple questions, what, why, when, how, where, and who, are the fundamental tools they use every single day to track down a disease and protect all of us.
All right, so here's our case file for today. First, we're going to meet the detectives themselves. Then, we'll see how they count the clues and start investigating the scene. After that, we'll get into the toughest part, how they actually prove their case. And finally, we'll see how closing the case can literally save millions of lives.
Okay, first things first, who exactly are these disease detectives, and what is their mission, really?
So this is the official kind of wordy definition. Let's break it down. Distribution. That's just detective speak for the who, where, and when. Determinants. Well, those are the why and the how. But you know, the most important part is right there at the end. This isn't just about studying problems, it's about taking action to solve them. And this might be the most famous case in the history of the field. Back in 1854, a doctor named John Snow was up against a deadly cholera outbreak in London. Now, he didn't know about bacteria yet, but he did what any good detective would do. He made a map. He marked exactly where people were getting sick and saw this terrifying pattern. All the cases were clustered around one water pump. By simply removing the pump handle, he stopped the outbreak in its tracks. It's just a brilliant, classic example of how finding the where can lead directly to saving lives.
Okay, so before any detective can find the culprit, they have to assess the scene. For an epidemiologist, that means you've got to get a handle on the numbers. These are the first 2 critical questions you have to ask. Answering them helps officials understand just how serious an outbreak is and how they need to respond. And to do that, they rely on 2 key measurements.
All right, so these 2 are incidence and prevalence. They might sound similar, but they tell you very different things. Think of it this way. Incidence is all about speed. How many new cases are popping up? It tells you your risk of getting sick. Prevalence, on the other hand, is like a snapshot. How many people in total are sick right now? That measures the overall burden of the disease on a community.
And this bathtub analogy makes it perfectly clear. Just think of incidence as the new water flowing into the tub from the tap. Prevalence is the total amount of water that's actually in the tub at any given moment. And of course, when people recover, or sadly pass away, that's like water draining out. It's a super simple but really powerful way to picture the difference.
Okay, so our detectives have measured the scale of the problem. Now comes the real legwork, hunting down the culprit.
And this is the central mystery, isn't it? It's one thing to count the cases, but it's a whole other challenge to figure out what's causing them in the first place. To crack this, epidemiologists have 2 main strategies they can use.
Essentially, they can either work backward in time or they can work forward. A case control study works backward. It starts with people who are already sick, the cases, and compares them to healthy people, the controls, to figure out what was different in their past. A cohort study does the opposite. It works forward. It starts with a group of people, tracks their exposures, and then follows them over time to see who gets sick.
So, to quickly sum it up, a case control study is fast and pretty efficient, especially if you're looking at a rare disease, since you can start with a handful of people who already have it. A cohort study, though, is the gold standard for testing a specific idea like, does smoking really cause cancer? But the big trade-off is that it's slow and expensive. I mean, it can take years, sometimes even decades, to get an answer.
And now we get to what is probably the highest hurdle in any investigation. Just because 2 things seem to be linked doesn't mean one actually caused the other. The detective has to prove it beyond a reasonable doubt.
This is the million-dollar question. I mean, think about it. Ice cream sales and shark attacks are definitely associated. They both go way up in the summer. But eating ice cream doesn't cause shark attacks, right? The real cause is the summer weather itself, which gets more people in the water and gets more people eating ice cream.
This is one of the most important rules in all of science, period. Mistaking a simple association for a real cause can lead to really bad policies and dangerous health advice. So, how do epidemiologists get it right? Well, they use a pretty rigorous checklist to build their case.
So, to build a really strong case, these detectives look for several key pieces of evidence. First,
Temporal relation. The cause has to happen before the effect. Makes sense. Second, strength. The link needs to be statistically strong, not just some random fluke. Third, dose response. More exposure should lead to a higher risk. Smoking 2 packs a day is way riskier than 2 cigarettes a day. And finally, consistency. The same finding has to pop up again and again in different studies with different groups of people.
Okay, so once the evidence is overwhelming and the cause is proven, the case isn't really closed. In fact, you could argue the most important part is just beginning, turning all that evidence into real-world action.
Because you have to remember, the entire point of all this painstaking detective work is to use that knowledge to prevent and control disease. The ultimate goal, always, is protecting public health.
And one of the most powerful public health tools that comes from all this is the concept of herd immunity. The idea is actually pretty simple. When enough people in a community are immune to a disease, a virus or bacteria just runs out of places to go. It keeps hitting dead ends, which creates this invisible protective shield for the most vulnerable people who can't get vaccinated themselves.
And the results of this work? They can be absolutely world-changing. Smallpox, a disease that killed hundreds of millions of people throughout history, no longer exists in the wild. It was declared completely eradicated back in 1980, all thanks to a global vaccination campaign. It's truly one of the greatest triumphs of public health ever.
And this is just a short list of the incredible victories. From the very first vaccine for smallpox all the way up to the mind-blowingly fast development of the COVID-19 vaccines, every single one of these breakthroughs was made possible by the patient, difficult detective work of epidemiologists who first had to figure out who the enemy was and how it spread. The work of these disease detectives is never really done. There are always new challenges popping up, from chronic illnesses like Alzheimer's to the constant threat of the next pandemic. The tools and methods they use are always getting better, but their fundamental mission, that stays the same: to answer those simple questions: what, why, when, where, how, and who, all to protect us.